Hello. I will be covering the first section today from chapter 1. So chapter 1 is going to be about problem-solving strategies. So I'm going to write this down. Okay, so chapter 1. It's on problem-solving strategies and principles. And the first section is on problem-solving strategies. So the title is problem solving. So we're going to see 13 strategies. Okay, so in this section, we cover 13 problem-solving strategies. Okay, so the goal in writing the section is to introduce you to some practical techniques and principles that will help you to solve many personal and professional problems in your life. And these problem-solving strategies are going to keep coming back when you're doing the assignments. Later on in the next chapter, you're going to see, okay, what problem-solving strategy am I going to use? So much of the advice presented in this section is based on a problem-solving process developed by the eminent Hungarian mathematician George Polya. So he wrote a book, and he wrote a book in which he outlined the problem-solving method. So it has 4 basic steps. Well, actually 3. The first one is to understand the problem. The second one is to devise a plan. And the third one is to carry out your plan. Okay, so the first strategy is drawing pictures. Oh, actually, there are 4. The fourth one is to check your answer. So yes, there were 4. So the strategy number 1 is to draw pictures. Problems usually contain several conditions that must be satisfied. You will find it useful to draw pictures to understand these conditions before trying to solve the problem. For example, this is number 2 at the end of the section. All you need to do is draw a picture. You don't need to solve anything. You are just drawing a picture. So I'm going to copy the directions, and I'm doing number 2. So this on page 15. So I'm writing down the page. Okay, the situation is that 5 people clink each other's glasses in a toast. And all we're doing is drawing a picture. We're not solving any problems. So let's say we have 5 people. We're going to call them A, B, C, D, and E. It says 5 people clink each other's glasses in a toast. Okay, so person A corresponds to 4 people. Then person B, A to B is the same as B to A, but B corresponds to C. Yeah, I'm going to indicate this with dots. Corresponds with C, with D, and with E. Then AB is the same as BA. Well, I already did that. And AC is the same as CA. BC is the same as CB. So we have left BD and BE. And then person D, AD is the same as DA. DB is the same as BD, and DC is the same as CD. So I have left DE. And that's it. We're not solving anything, we're just drawing a picture for the situation. The second strategy is to give names to unknowns. It is good practice to name the objects in a problem so you can remember their naming easily. So also on page 15, we have example number 8. So I will copy the directions and the problem. We're not solving the problem. We're not solving a problem. We're just giving names to unknowns. We're choosing appropriate names for unknowns. Okay, so choose good names that will be meaningful for each item. Again, you are not being asked to solve the problem. Just make a recommendation for some good names. Patrick Mahomes wants to include more calcium and protein in his diet. So he will decide how many grams of protein and how many milligrams of calcium. So we can name two unknowns. We can just let C represent calcium. And P represent protein. And that's it. That's all we need to do. Just give names to unknowns. So we have two strategies so far. The third strategy is to be systematic. If you approach a situation in an organized, systematic way, frequently you will gain insight into the problem. So we're looking at example 4. We're still on this page 5. Okay, Nico is considering which optional features to include with his new smartphone. He has narrowed it down to 3 choices: multiple screens, multiple cameras, and artificial intelligence photo editing. Depending on price, he will decide how many of these options he can afford. In how many ways can he make his decision? So we're going to use strategy 2 in the process. We're going to organize the information, but we're also going to use the second strategy. We're going to give names to unknowns. So let's call S. So we have 3 choices: multiple screens, multiple cameras, and artificial intelligence, photo editing. So let's give names to unknowns. Let's call S multiple screens. C, multiple cameras. And we're going to call A, artificial intelligence photo editing. Okay, so Nico has the following possibilities. That the phone has none of these features. Obviously, the more he has, the more he will pay. But his phone may have no features, one feature, two, or three. And it can happen in the following ways. So we gave names to unknowns. S stands for multiple screens, C for multiple cameras, and A for artificial intelligence photo editing. So if the phone has no features, it means it doesn't have any of the three. If the phone has one feature, that can happen in three ways. That it has one, but not the other two. So I'm going to start with multiple screens, but not the other two. If it has two features, that can happen in also in three ways. So it has two, but not a third one. So it may have multiple screens and multiple cameras, but no AI photo editing, or it may have multiple screens and AI photo editing, but no multiple cameras, or it may not have multiple screens, but have the other two. And if it has all three, that can only happen in three ways. So at the end, if you count the choices, he has 8 ways. Let's read the problem again. So in how many ways can he make his decision? So Nico can make his decision in 8 ways. So that was strategy number 3. Okay, so the next example is the combination of the previous two, drawing pictures and being systematic. So you can organize the information in a tree diagram. Actually, I did first example 3, and then I'm going back to example 2. Okay, so while making a donation, okay, I'm making sure that I'm sharing. I think I am. While making a donation at your campus blood drive, you discover that your blood type is AB minus or AB negative, and your friend Brian's type is O positive. Your type means that you possess both the A and B antigens, and the negative sign indicates that you lack the RH antigen. So type O means that Brian lacks the A and B antigens, but the plus sign indicates that he does have the RH antigen. Example 2 shows an effective way to visualize all blood classifications involving those three antigens. Okay, so by combining the strategies, drawing pictures, and being systematic, we can create a tree diagram, which consists of drawing all the possibilities. So this is on page 4. So draw a diagram to illustrate the different blood classifications possible if we're considering only the A, B, and RH antigens. Okay, so all the possible blood types with these antigens. So we can organize it as if the blood possesses the antigen A, that it possesses B, and whether it possesses RH. Okay, so we begin. So the blood type may or may not possess A. So we have two choices, yes or no. A for B and RH. So it may or may not possess B. And it may or may not possess RH. And I have 4 more. And the last 2. So I'm not going to draw down, I'm not going to write down the blood types, but now you can see the possibilities. AB positive, AB negative, A positive, A negative, B positive, B negative, and typo positive and typo negative. So the conclusion is that there are 8 possibilities. So in chapter 12, we're going to study counting techniques. But yeah, each there are two possibilities for each antigen, that it has it or it doesn't. And if you multiply the possibilities, you get the total number of possibilities. But we did it with a tree diagram. Strategy number 4. So a lot of math is about patterns. That's going to be strategy number 4. That's on page 6. So a lot of math is about patterns. And if you can recognize a pattern in a situation you're studying, you can often use it to answer questions about the situation. So back to page 15. We're doing number 20. We're doing number 20 and 21. Okay, so those are the directions. Let's do number 20. Okay, so in exercises 19 through 24, continue the pattern. This, by the way, page 15. Page 15. In exercises 19 through 24, continue the pattern for 5 more items in the list. There may be more one way to continue a pattern, and the book provides only one solution. So number 20, the first 4 terms are 1, 3, 9, and 27. So if you can see the pattern, the previous number is multiplied by 3. So that's how we're going to get the next 5. So 27 times 3 is going to be 81. 81 times 3 is 243. 243 times 3 is 729. 729 times 3 is 2,187. And 2,187 times 3 is 6,561. Number 20. Well, number 20, there was only one way to continue that pattern. In number 21, there might be more than one way. So they give you the first 7 terms. Those are AB, AC, AD, and AE. Next, they do BC, BD, and BE. So we're going to write 5 more terms. Okay, so we have the first 4 terms was the letter A, followed by the next 4 letters. And then we have B, followed by the next 3 letters. So from what we can see, the next one would be BF. Next, we have C, and the 4 letters following C. So those are CD, CE, CF, and CG. There might be another way to solve it, but this is the one that the book has. So it's that letter and the following 4 letters. Strategy number 5 is to draw a simple version of the problem. So that's on page 7. You can begin to understand a complex problem by solving some scaled down versions of the problem. Once you recognize a pattern in the way you're solving the simpler problems, you can carry over this insight to attack the full-blown problem. So same page, we have number 6. Okay, suppose that 12 branches of Bank of America need secure communication links among them so that financial transfers can be made safely. How many links are necessary? So rather than trying to answer the answer for all 12, that might be a lot. What we are going to do is start with a smaller number. Let's say we start with 2, then 3, and so on, and find a pattern to determine the number of links. So instead of trying to answer for all 12 branches, start with a smaller number. Then we're going to use one of the previous strategies. We're going to find a pattern to answer the question for all 12. So we're using some of the previous strategies. We're being systematic, we're finding patterns, we're giving names to unknowns. So we're using a few of those. So we're going to organize the information by the number of branches, then the branches themselves, the links, and the number of links. Okay, so if it has one branch, let's call the branch A. Well, there's no way to link a branch with itself. So one branch has no links. 2 branches are going to have one link. Let's call the branches A and B. So there's only one link, which is AB. AB is the same as BA. So there's only one link. If it has 3 branches, and we link them in pairs, the branches are A, B, and C. And the links are AB, AC, and BC. Number 4. So still the pattern isn't clear. Let's do another one, or let's increase it to 4. The links are now AB, AC, and AD. Then AB is the same as BA. We're not linking B with itself. We have next BC, BD. Then AC is the same as CA. BC is the same as CB. The last one is CD. So we have 6 branches. Okay, let's separate this. So if the pattern still doesn't look clear, we are going to add one more. What happens if we have 5 branches? And how many links do we have? Okay, so the links are going to be AB, AB, AC, AD, and AE. Next, BC, BD, and BE. The one starting with B. The next ones are CD and CE. And the last one is D. So that's a total of 10 branches. Okay, so I'm now going to give the pattern now, but let's see. We started with 1, and then we added 1. Then, so 0 plus 1 is 1. 1 plus 2 is 3. Then 3 plus 3 is 6. 6 plus 4 is 10, and so on. If this pattern continues, the next one would be 15. Okay, so here's the question. What about the 12 branches? Okay, so I'm going to make a smaller table with the number of branches. And the number of links. So we found that for 0 branches, there are no links. For 2 branches, there is 1 link. For 3 branches, there are 3 links. For 4 branches, there are 6 links. Then for five branches, there were 10 links. So if we want to do it for 12, we now can identify the pattern. So I'm going to go all the way to 12. Okay, so 1 plus 0 is 1. 2 plus 1 is 3. 3 plus 3 is 6. 4 plus 6 is 10. 5 plus 10 is 15. Then 6 plus 15 is 21. 7 plus 21 is 28. Um, 8 plus 28 is 36. 9 plus 36 is 45. Then 10 plus 45 is 55. And 11 plus 55 is 66. At the end, for the 12 branches, there will be 66 links. So for 12 branches, there will be 66 links. Okay, so we have done, as of now, we have done 5 strategies. There's a total of 13. Strategy number 6 is that guessing is okay. Now, this is not the most convenient one. If you have another method to do it, go ahead with it. But if um, if you don't know any other mathematical tool to solve a particular problem, guessing is okay. That's page 8. Okay, so I'll copy this again because I have something that shouldn't be there. So let's take this out. Let's try again. Okay, that's better. So one of the difficulties in solving word problems is that you can be afraid to say something that may be wrong and consequently sit down staring at a problem, writing nothing until you have the full-blown solution. Making guesses, even incorrect guesses, is not a bad way to begin. It may give you some understanding of the problem. Once you make a guess, evaluate it to see how close you are to meeting all the conditions of the problem. So I'm going to do number 58 on page 16. Okay, the situation is that Carlos has $9,000 in two mutual funds. One fund pays 11% interest, and the other fund pays 8% interest. If his income from the two funds last year was $936, how much did he invest in each fund? Okay, so if we know if we know how to solve systems of linear equations from algebra, this would be the best way to do it. But let's suppose for now that we never learned how to solve systems of linear equations, two systems of two equations into variables. Let's suppose that we have never done that, and we're going to solve this problem by guessing. So we're going to call A. Actually, I don't need to give names to unknowns. So what I'm going to do is, 11%. There's actually a section on percents later on. 11% as a decimal is 0.11, and 8% as a decimal is 0.08. Okay, so we are going to start with each fund having the same amount. So we're going to begin with the 11% fund. Let's see. Okay, so begin with 4,500 in the 11% fund and 4,500 in the 8% fund. So we are dividing the 9,000 into half and half. Okay, so let's see how much interest is that. That's going to be 4,500 at 11% plus 4,500 at 8%. So if you add that, that's going to be $855. Okay, so we are falling a little bit short of the 936. So we are going to increase the amount of the 11% investment. The one that pays more, we're going to increase the amount to get closer to, well, to increase the amount of interest. So increase the amount in the 11% investment. So we started with half and half. We're going to increase this to 6,000 and 3,000. Okay, so 6,000 at 11%, that's going to be 660. And 3,000 at 8% is going to be 240. That's going to be for a total of $900. We're still falling short. But let's organize this in a table with what we have already. We have the guesses. I'm going to rewrite this. We have the guesses. We have the interest amount. So the first two guesses were 4,500 and 4,500. And we found that the interest amount was 855, which was below the amount of interest that we're looking for. We increased the 11% fund to 6,000, and the 8% we decreased it to 3,000. And we found that the interest was 900. Okay, so we are going to increase it now to 7,000 and 2,000. Okay, so 7,000 at 11% plus 2,000 at 8%. And the interest amount is 930. Okay, so we are getting close. We're getting close to 936. So instead of increasing it by 1,000, since we are $6 below that, we're going to increase it by 100. We're going to increase the 11% investment to 100, or by 100. And that is going to be 933. Okay, so we are close. That increased from 930 to 933, and we want to have 936. So it looks like we're on the right track. Let's increase it by another 100. And if we are above, we're going to start decreasing then by amounts of 10. And so that's 1,800. So if you calculate this, you'll find that the interest amount is 936. So at the end, we find that he invested 7,200 at 11%. And 1800 at 8%. Now, this is not the most recommended strategy if you know another way to, a more direct way to solve this problem. Like a more direct way to solve this problem is by setting up a system of two linear equations rather than trying to guess the solution. Strategy number 7 is to relate a new problem to another one. Okay, an effective technique. This is on page 9, strategy number 7. An effective technique in solving a new problem is to try to connect it with a problem you have solved earlier. It is sometimes possible to rewrite a condition so that the problem becomes exactly like one you have seen before. So I'll copy the next problem. That's number 65. Okay, so assume that Menaka has determined the following possibilities for classes for her next semester schedule. She can take math at 9, 10, or 11. English at 9, 11, or 12. Sociology at 10 or 12, and art history at 9, 10, or 11. Determine all the possible ways that Menaka can schedule these classes. So relating that new problem to another one, we're going to draw a tree diagram. Okay, we're going to draw a tree diagram. We're going to call these courses, we're going to give them names. We're going to call M stands for math. E stands for English. S stands for sociology. And A stands for art history. Okay, so I'm just going to open more space. So we're going to draw a tree diagram for this problem. Okay, at what time she can take math, English, sociology, and art history. So we can see that she can take math at 9, 10, or 12. So if She took math at 9. She cannot take English at 12. I mean, she cannot take English at 9. If she took math at 9, she can only take English at 11 or 12. Those are her options for English. So if she took um, math at 9 and English at 10, she has two choices for sociology. She can take sociology at 10 or 12. So if she took math at 9, English at 11, sociology at 12, she cannot take art history at any of these times. So that's not possible. If she shows math at 9, English at 11, and sociology at 10, or sociology at 12, she can take art history at 10. Now, let's suppose that she schedules math at 9 and English at 12. So she can take sociology at 10. And art history at 11. Now, if she schedules math at 10, she has three choices for English. She can take English at 9, 11, or 12. So if she takes math at 10 and sociology at 9, sorry, math at 10 and English at 9, she can take sociology at 12. And art history at 11. If she takes math at 10, English at 11, she can take sociology at 12. And art history at 9. If she takes math at 10 and English at 12, well, she cannot take sociology. And finally, if she takes math at 12, she can take English at 9 or 11. Okay, so math at 12, English at 9, she can take sociology at 10. And art history at 11. And finally, math at 12, English at 11, she can take sociology at 10, and art history at 9. So if we count the possibilities, she can do this in 6 ways. Okay, so we have covered 7 problem-solving strategies. The last, okay, so we have covered 7, we have 6 left. But the ones remaining are some mathematical principles. And that's the next strategy, strategy number 8. This on page 11 is called the always principle. Okay, so this is page 11. When we say that a statement is true in mathematics, we are saying that the statement is true 100% of the time. One of the great strengths of mathematics is that we do not deal with statements that are sometimes true or usually. So if you find an example for which the statement is not true, the statement is false. Let's do example 9. So find an example to illustrate that the statement x plus y squared equals x squared plus 2xy plus y squared is true. So that one is true for any two real numbers. So we can let x be 4 and y be 5. And we're going to compare both sides. Left-hand side. 4 plus 5 squared. Okay, so 4 plus 5 is 9. And 9 squared is 9 times 9. And right-hand side, this is what? This is 4 squared plus 2 times 4 times 5 plus 5 squared. Now, 4 squared is, and actually I'm going to talk about the order of operations. So first we need to do the multiplications and then we're doing the sum. 4 squared is 16. 2 times 4 is 8. 8 times 5 is 40. And 5 squared is 25. So the sum is indeed 81. Strategy number 9 is the counterexample principle. So in this example, in the always principle, we say that a statement is true 100% of the time. If you find a situation for which this is not true, that situation is called a counterexample, and that makes the statement false. So same page, page 11, an example that shows that a mathematical statement fails to be true is called a counterexample. Keep in mind that if you want to use a mathematical property and someone can find a counterexample, then the property you're trying to use is not allowable. 100 examples in which a statement is true do not prove it to always be true. Yet, a single example in which a statement fails makes it a false statement. Be careful to understand that when we say that a statement is false, we're not saying that it's always false. We're only saying that the statement is not always true. That is, we can find at least one instance in which it is false. So let's do number 10. Okay, although the following statements are false, those who are not secure in working with algebra often believe them to be true. And actually, they are going to be true in some cases. Like if you let one of the numbers be 0, then the statement is going to be true. But in general, it's going to be false. So yeah, you can find some instances for which this is true. But that doesn't make the statement true. So in A, Let's suppose that x is 3 and y is 4. The left-hand side is going to be 49. So order of operations, first we simplify whatever is inside parentheses and then we multiply. And right-hand side, that one is going to be 9 plus 4, 9 plus 16. So that is 25. Now we can see that this is not true. We found two examples or two numbers for which this statement is not true. Or we found a counterexample for part A. For part B, now we're going to let x be 9 and y be 16. The left-hand side is the square root of 9 plus 16. Square root of 25 is 5. The right-hand side, that's the square root of 9 plus the square root of 16. And that is 7. So again, we found a counterexample for these two statements. Okay, strategy number 10. Is the order principle, in particular, the order of operations. So yes, the order in which you do operations is important. When you read mathematical notation, pay careful attention to the order in which the operations must be performed. The order in which we do things in mathematics is as important as it is in everyday life. When you get dressed in the morning, it makes a difference whether you first put on your socks and then your shoes, or first put on your shoes and then your socks. Although the difference may not seem as dramatic, reversing the order of mathematical operations can also give unacceptable results. Note that we're not saying that it is always wrong to reverse the order of mathematical operations. We are saying that if you reverse the order, you may accidentally change the meaning of your calculations. Okay, so the order of operations. The order of operations is that you first do parentheses. So start with parentheses. Okay, once you simplify the parentheses, work with exponents. Exponents, and that include radicals or roots. Like square roots. The next is multiplication and division. The next operation in the order is multiplication and division. And finally, addition and subtraction. So one way to the shortcut to remember the order of operations is the word PEMDAS. Or sometimes they say, please excuse my dear Aunt Sally. So that's P E, M, D, and A, S. Okay, so in the last example, we saw that x plus y squared does not equal x squared plus y squared. You need to first simplify x plus y in the parentheses and then square the numbers or multiply that number by itself. The other example I did was the square root. The square root of x plus y is not square root of x plus square root of y. Because the order of operation matters. First, you need to simplify whatever is inside the square root, and then take the square root. Okay, we have three more. Strategy number 11. That's on page 13. It's called the splitting hairs principle. So that's page 13. So you should split hairs when reading mathematical terminology. If two terms are similar but sound slightly different, they usually do not mean exactly the same thing. In everyday English, we may use the words equal and equivalent interchangeably. However, in mathematics, they do not mean the same thing. The same is true for notation. When you encounter different looking notation or terminology, work hard to get a clear idea of exactly what the difference is. Representing your ideas precisely is part of good problem solving. So in example 12, we can see things that look similar, but slightly different. They usually do not mean the same thing. Okay, so in example 12, we have two pairs of symbols that look similar, but look slightly different, that they don't mean the same thing. Part A, I'm sure you're familiar with that. So the symbol on the left is less than, and the symbol on the right is less than or equal to. In B, the symbol on the left that represents the intersection of two sets is a rounded symbol, and the one on the right is a pointed symbol. We use that for true and false statement, which I'm not going to cover, with truth tables that I'm not going to cover in this course. In part C, the symbol on the left has an extra line. So we're going to be using those in sets. When we cover chapter 2, when we cover sets, we're going to be using those two. And in D, the one on the right is number 0, and the symbol on the left is something else that we use in set theory. But that is not a number. Number 12 is the analogous principle. So that's on page 13. Much of the former terminology that we use in mathematics sounds like words that we use in everyday life. This is not a coincidence. Whether you can associate ideas from real life with mathematical concepts, you will better understand the meaning behind the math you are learning. Okay, so I'm just going to read this example directly from the book. So in the table below, the left column contains formal mathematical terminology. The right column contains ordinary English words that will help you remember the mathematical concept. So we're going to be talking, the first three, we're going to be using them in sets. Union means putting things together, like labor union, marriage union, or united, like the United States. Complement, the idea of complement is that we are completing something. We're going to be using that word in chapter 2. Equivalent means that in some way, things are the same. And slope, in chapter 7, we're going to talk about the slope of a line. So the idea could be a ski slope or the slope of a roof. And the last one is strategy number 13. So this is the last one. With this, I finish the section. It's the three-way principle. So I'm just reading this from the book. Let's zoom out just a little bit so you can see it. So let's do this a little bit more. Okay, we conclude this section with a method for approaching mathematical concepts that we illustrate in figure 1.6. That is the figure you're seeing there. Whether you are learning a new concept or trying to get insight into a problem, it is helpful to use the ideas we have discussed in this chapter to approach mathematical situation in three ways. Verbally, that is by making analogies. State the problem in your own words. Compare it with situations you have seen in other areas of math. Graphically, by drawing a graph or a diagram, and by example, by making numerical and other kinds of examples to illustrate the situation. So not every one of these approaches fits every situation. But if you get in the habit of using a verbal graphical example approach to doing mathematics, you will find that math is more meaningful and less dependent on rote memorization. If you practice approaching mathematics using the strategies and principles that we have discussed, you will find eventually that you are more comfortable and more successful in your mathematical studies. So thank you for listening.